So welcome everybody to our Northridge Earthquake 30 years later, our Northridge 30 webinar series titled The Northridge Earthquake 30 Years Later, a Catalyst for Engineering Resilient Communities. This series is organized by a number of different people in these various organizations: the American Society of Civil Engineers Infrastructure Resilience Division, the American Society of Civil Engineers Los Angeles section, the Earthquake Engineering Research Institute Southern California chapter, the Structural Engineers Association of Southern California, and the Earthquake Country Alliance, which is led by the statewide California Earthquake Center. This is episode 3 that you'll be viewing. We've had the prior 2 episodes. The first one on titled the January 17th, 1994 Northridge Earthquake on Science and Engineering Aspects. Episode 2 came about a month and a half later on insurance issues and impacts following the Northridge Earthquake. Both of those are available. They were recorded and available online at these links at the Earthquake Country Alliance. And also they're available on the EERI Southern California branch website. And now I would like to introduce Sam Megonko. He's from Structural Focus and currently serves as the EERI Southern California branch president.
Thank you, Craig. Today's webinar is titled 30 Years of Progress in Quantification of Seismic Hazards. There's been an exponential progress in the quantification of seismic hazards since the Northridge earthquake. In this webinar, after a brief review of the status of seismic hazard in the 1994 era, we'll do an overview of the progress in our understanding and quantification of ground motion hazard. One major development in the direction of seismic hazards research in the last 30 years has been the initiation and expansion of a series of large community-based research programs on earthquake hazards. These non-traditional collaborative research initiatives have resulted in major advancements in our understanding and modeling of geohazards, and with a wide spectrum of impacts on various issues in earthquake engineering. In this webinar, 2 examples of such large community-based programs will be presented: NGA Ground Motion Research Series and Fault Displacement Hazard Initiative will be overviewed along with their current status and directions. I'd like to introduce Dr. Yusuf Borzogna, who will be our speaker today. Yusuf Borzogna is a professor at UCLA Department of Civil and Environmental Engineering, and he is the director of the Natural Hazards Risk and Resiliency Research Center, which is known as NHR3. Dr. Borzogna's decades of experience and expertise include earthquake engineering and ground motion hazard, with an emphasis on multidisciplinary aspects of earthquake science and engineering. He has extensively published scientific papers on earthquake ground motion models, seismic hazard analysis, and earthquake engineering. Dr. Borzogna is a licensed professional civil engineer in the state of California and has been a fellow of the American Society of Civil Engineers since 1998. Dr. Borzogna has been the principal investigator of multiple phases of the NGA seismic hazard research programs. In 2019, EERI, Cosmos, and SSA jointly awarded Borzogna with the Bruce Bolt Medal for his extensive contributions to seismic hazard analysis and earthquake engineering. In 2023, Borzogna was awarded the UCLA Public Impact Research Award for his decades of impactful research contributions. Dr. Borzogna, take it away. Thank you.
Thank you, Sam. Let me share my screen to hopefully it works. I'm assuming you're seeing my slide. Is that right, Sam?
Yes.
Very good. Thank you very much, Sam. When Sam was reading that, at one moment it crossed my mind who is the person he's referring to, but then I found out. So thanks so much for kind introduction. So I'm going to talk about the progress, very high-level progress that we have had it in the last literally 30 years on ground motion, databases, models, hazard, and as well as fault displacement hazard, and a summary also. Before we start, I want to apologize that I'm not be able to mention tons of important contributions in the last 30 years. It's impossible. I need 30 days rather than 30 minutes. So for sure, I know for a fact, I'm going to miss lots of important contributions because of the lack of time and that it's impossible to cover it. So let's talk about ground motion progress in ground motion models. Ground motion models, GMMs, also we used to call it ground motion prediction equations. Basically, they are models to scale ground motion, level of ground shaking with respect to magnitude, distance, soil condition, hanging wall, footwall, and lots of other parameters. For active tectonic regions like Western US, most of the Western US, the models are mainly based on observations or empirical data, or in other words, recorded ground motions. But physics-based simulations have important role, which I'm going to mention it also. So let me just show one slide, only few historical ground motion models that developed in the last decades. First, I want to mention 1964 ground motion model by Luis Esteban and Emilio Rosenblum. This was important both in terms of his technical importance, as well as importance of the role of this model in forming PSHA, probabilistic seismic hazard analysis, that Alan Cornell developed and published in 1968. And if you go through Alan's paper, you see that repeatedly he's referring to that model 1964. And then Luis Esteban also continued that model later on. That's a very interesting historical story that later we can talk about. It's a very nice historical story. Then bunch of California-based ground motion models. Again, there are much more than that. I know it. I'm just mentioning three of them. Ross Sadiq had important ground motion model. Ken Campbell started in 1981, and then Johnny Rambor, 1981. If you open BSSA volume issue in 1981, you see two papers back to back by Chen and Joyner and Bohr. And as I mentioned, I know it that there are lots of more contributions that I'm not listing it here. So then Northridge happened, obviously very well recorded event. It was a very important event, not only for the structural engineering, geotechnical engineering, also in terms of recorded ground motions. And also it was a very important local ground motion for us, reverse faulting, that it did a contrast between hanging wall and footwall that we still count on the data recorded during the Northridge earthquake. What we had in 1994, in terms of distance, we had Joyner and Bohr distance, seismogenic distance, and so on. In terms of soil conditions, most of the models had hard rock, soft rock, steep soil, soil. They more started using VS30 scaling in ground motion models. And the concept of the magnitude saturation that the Ken Campbell emphasized in his 1981 paper was acceptable by most or some researchers. That was the evolution of really ground motion modeling. A style of faulting was recognized as important. This is a plot that showing a strike versus reverse, obviously crude. The paper published in 1993, just few months before the Northridge earthquake. So the importance of a style of faulting was becoming known to the researchers. This is really important point that I want to make here. In 1994 era, the traditional seismic hazard research was individual researcher or a small group of researchers coming together. The interactions among the ground motion modelers were relatively minor. They knew each other, they were following the work of each other, but not much interaction. They were competing with each other, which is good, but not much interaction. Then what we have now in 2024, in the last 30 years, is really major expansion of the community-based research project, as Sam read it in the introduction. This is a big deal. I really think this is a big deal. The community-based projects broke the wall between the research teams. So research teams, they learn from each other. They still compete with each other, which is great, but the quality goes up due to its extensive interaction and learning from each other. I really think this is one of the most important things that has been happening in the last 30 years. In 2024, we have very strong constructive interactions among modelers, junior and senior researchers. Always graduate students are involved. Even undergraduate students, they work on the database development. Very importantly, practitioners are involved, because this kind of the research is not an abstract research. Really, the research is impactful. Therefore, the modelers, they like to really hear from the end users and practitioners. So their interactions are truly, I truly believe that have resulted in higher quality of the database as well as models. There are some interactions between ground motion experts and engineers, but I really think we need much more. These two groups, because I worked with both groups, they talk different languages. There are lots of misunderstandings that in the next N years, we need to expand the interaction among the earthquake ground motion experts and engineers. I really think this is another important thing for the future that we have to emphasize and expand. So I'll give you examples of the major technical progress in ground motion modeling for the shallow crustal earthquakes. Obviously, I have to mention NGOS1, NGOS2. So NGOS1, that at the time, it was not called NGOS1, it was called NGOS because no one imagined that it's going to go to NGOS2, NGOS3, and so on. So it was only NGOS, initiated in October 2003 and finished in 2008. USGS adopted the ground motion models, and the models went to the national hazard maps. It was a major big deal at the time. And then NGOS2 was a follow-up of NGOS or NGOS1, which was completed in 2014. So let me give you a contrast about the evolution or revolution in terms of expansion of the database. A typical database in 1994 era had this kind of data points: magnitude versus distance. Each point is one of the stations and earthquakes that we had at the time. So for ground motion in horizontal direction, for example, a typical database has a few hundred recordings, 40, 50, 60 earthquakes. In vertical, much less, because at the time, lots of instruments, they didn't record vertical components. Now, let's take a look at what we have done in the last 30 years. This is a database that we had in 1997, few years after the Northridge. Vertical axis is magnitude, horizontal axis is distance. So it means each point is a representative of a recording station that recorded ground motion at such and such magnitude and such distance. Then NGOS or NGOS1 came in. The database increased a lot. And then NGOS2 came in, and the ground motion increased by a very large margin. As we speak, NGOS2 has about 21,000 three-component recordings, so it's about 60,000+ records. Then, sorry. So in terms of modelers, a typical modeler team used like +600+ recordings for the modeling. For 2014, a typical NGOS 2 can use more than 15,000 recordings. So the size of the data used to develop models increased by a factor of 20 or 25, not 10%, 20%, 30%. It's a huge increase as you see the exponential growth of the size of the database. Now, we are in the middle of another large community-based project, NGOS3. The size of the database from NGOS2 is now being increased by a factor of 5. So it's unbelievable. We are in the middle of really huge big data in ground motion modeling. So another big point that I really want to contrast between where we are now and 1994 is that the availability of the database. In 1994 era, most ground motion modelers, they have their own databases, and the databases mostly were not public, with the serious exception of the USGS, because they always had a public database. So the individual teams, they basically owned the database. Now in 2024, the databases merged in the last 30 years, and now we have one big database which is basically available in terms of intensity measures, in terms of peak ground acceleration, peak ground velocity, pseudospectral accelerations, and so on. So the rule has been in the last 20+ years that I have to give the credit to Dave Bohr. 20+ years ago, he said, any ground motion model that we develop, the data that we use for that ground motion model should be available to public. And we follow that constitution, and we make all the flat files of the NGA available to the public. And then another advantage of merging multiple small databases into one big database is that the database is now checked on a weekly basis, and lots of errors are found, and lots of errors are checked and resolved. So that's another advantage that we are in 2024 versus 1994. Let's take a look at the models that we had in 1994 era. This was a typical model that we had by different modelers. They have a little bit different, but that's a few terms that they had it in 1994. Now, the current typical NGA model, this is the model that we have. It looks scary. I agree. It looks scary. It's much more complicated, but the intention was never to make it complicated for the sake of complications and publishing a paper. That was never intention by any modelers. The intention was really to capture various features of the observations as much as possible. For example, animal and football. We see the contrast. We are going to make a model for that, and as well as lots of other features. So more features we observe in the data, in the nature, we make it inside the model. That's why the models are becoming or they appearing more complicated. Then the current ground motion models that we have mostly for the crustal earthquakes, they are applicable to magnitude 3 to 8.5, most of the models. Distance 0 to 300 kilometers, again, most of the models. They include features of hanging wall, footwall, soil condition site from VS30 of 150 plus minus to 1500 plus minus meters per second. Soil nonlinearity is mostly included in most ground motion models. Deep basin effects mostly are included in the ground motion model. That's why you see the ground motion models are becoming more complicated. A style of faulting is now most of the ground motions, they have it. One advancements that the models, they made it, the models, most of the models, they go from PGA all the way to 10 seconds. Now, I see even in projects that the community is demanding, let's go even beyond 10 seconds. So we are growing as we speak. In 1994, the issue of vertical ground motion attracted the attention of some engineers. There were some collapsed bridges and one department store that I'm showing the photo. I visited that site, and some people, they attributed the collapse of these structures to vertical ground motion. Suddenly became a big issue. In 1994, we knew that the ratio of vertical over horizontal, V over H, is a function of distance as well as soil condition and so on. And we had a sense that using traditional V over H scaling of 2/3 is not going to work. For the graph that you see is an old graph, is a publication of 1992, a couple of years before the Northridge. Then Northridge happened, the loop was closed. We confirmed that using 2/3 to scale vertical over horizontal is not really defendable. It can be conservative, it can be unconservative, depending on the soil condition, distance, period, oscillator period, and so on. So immediately after that, it was a common recommendation, don't use 2/3 to scale horizontal to get vertical. Now in 2024, we have multiple vertical and multiple V over H models. They are all in very good shape, robust predictions, qualitatively consistent with previous work, but obviously not 100% quantitative. And I'm so proud to say that starting 2009, even vertical design spectrum kicked into the building code. It was not easy. It took a long time, lots of presentations at the structural engineering associations of Northern California, Southern California, and so on. But eventually, the building code writers, they recognized, and it went through building code. As we speak, vertical design spectrum is in the ASCE 7, both 16 and 22. As you know, most of our ground motion models, the recent ground motion models, are for 5% damping. That doesn't mean that your structural or geotechnical system has really 5% damping. Therefore, we needed damping scaling factors and the models. And with the leadership of Sanaz Rezayan of the USGS, now we have multiple damping scaling factors for horizontal component, for vertical component, crustal earthquakes, subductions, and so on. Everything is available to public. Then directivity of the ground motion in 1997, few years after Northridge, Paul Somerville and co-authors, I cut and paste the front page of that paper. They have published a very important paper on the directivity of ground motion models, on the directivity model, and the model has been extensively used in research and practice. It has also been updated multiple times. In 2024, We now have full probabilistic seismic hazard analysis, including multiple directivity models. You go to the website, you enter your site, you select which directivity model you want, and it's already built in the PSHA, not that you finish PSHA and then adjust it. Obviously, it's free of charge, and it's courtesy of Linda Al-Atiq, Nick Greger, and Silvia Mazzoni. There are thousands of maps already generated, and you can get PSHA for the directivity model that you like, and the ratio of the PSHA over PSHA with directivity over PSHA without directivity. Directivity is one issue that still has room for improvement for various reasons that we can discuss, but still it's not a closed issue. So now, if we go outside of the Western US, for Central Eastern North America, this is a slide that I borrowed from Christine Goulet, who is now with the USGS. Left-hand side is magnitude versus distance for the NGA West. Right-hand side is magnitude versus distance for NGA East. And obviously, in the relatively large magnitude and close distance, we don't have so much empirical data in the Central Eastern North America. Therefore, in NGA East, we cannot just fully rely on empirical data. Obviously, the modelers checked whatever they had against empirical data to make sure they don't violate the nature empirical data. But most models are heavily based on simulations. By 2015, multiple sets of models were developed, and both USGS and U.S. Nuclear Regulatory Commission started using these models. You see on the right-hand side is the cover page of a report by US NRC that they reviewed the models, and they had positive recommendation about the models. So I talk about Western US, then Central Eastern North America for the subduction, which is important for many parts of the world, as well as for Pacific Northwest and Alaska for the US. That was another large community-based project. You see the word of community-based, I use it multiple times in this presentation because really the process is extremely important. In this case, 34 people contributed to various pieces of the projects, including junior and senior researchers, practitioners, academics, and end users. So this is the database that we have currently in NGA sub, is a magnitude versus distance for different parts of the world. There are more than 200,000 records, over 6,000 recording stations in the database, magnitude 4 to 9.1, Tohoku, magnitude 9.1 in Japan. And this is the largest database among all NGA programs that we have before NGFS3. Now NGFS3 is going to even be larger than this database. Then the models, NGS sub, this is tradition of what we have been doing in the last 20 years as a community. The models have been adopted first of all by USGS for the Pacific Northwest and Alaska. The models have been coded in Visual Basic and is free. You can go to the website and you can enter traditional way, your magnitude, distance, and then you choose what model you want to use or what combination of models with weighted average. It gives you response spectra. So one thing that we did in NGFS3, different modelers, they did it differently, but the concept is common, that if there is a region that you have more data, then the uncertainty of median prediction, I'm not talking about aleatory variability, the median prediction, how much it can go up and down. if you have lots of data, for example, in the left figure and right figure in Japan, the median prediction, the uncertainty is not that huge. But if you go to another region like Cascadia, that we don't have so much data, the uncertainty of the median prediction can be large. Different modelers, they use different methodology to estimate that, but it is there. Then other intensity measures, so far we talked about mainly response spectrum and PGA, PGV, and so on. But in the last 30 years, we have had multiple other intensity measures. For example, Fourier amplitude spectra are becoming more and more important for the ground motion modeling. Right now, there are multiple FAS Fourier amplitude spectra models. There will be more by 2025. I want to make sure there is no misunderstanding. We are not abandoning response spectra. Response spectra are essential and critical for engineering applications. All we are doing is that in the process of ground motion modeling, we use Fourier amplitude spectra. They're easier to scale and manipulate it. But once the model is mature enough and is final, we are going to convert the model to PSA or response spectra. Engineers should not be concerned about that. It's only more advanced in terms of modeling. Final results that you're going to use still is going to be response spectra. Then other intensity measures, RDS intensity, CAV, Hausner spectrum intensity, you name it. There are multiple models of this other intensity measures, and we have now multiple very well-behaved models of these intensity measures around. Then I want to I show you one slide about everything that so-called we have been doing, both in research and practice. The process is that we generate a ground motion model or a set of ground motion models for a single degree of freedom elastic system, which is pseudospectral acceleration, basically. Then we develop hazard based on these models. And then we select a bunch of motions, ground motion motions, somehow compatible with the target, depending on what the methodology you use, how you scale it, how you modify it. Eventually, you're going to have a bunch of ground motion. And then we use these motions to excite nonlinear multi-degree of freedom system. So you see, we start with the elastic single degree of freedom system. We go through the process. At the end, we are going to use it for totally different thing. So the question is that, can we do something one step more realistic? Not that we are solving all the problems in the world. One step more realistic. Is a still single degree of freedom system, but instead of being linear elastic, is a nonlinear force displacement, restoring force. And this is one slide that we have Mahdi Bahrampuri has published, that magnitude scaling of the, say, maximum displacement for the elastic and inelastic response can be different when you get to large magnitude and large inelastic or large ductility. So that is the thing that we want to bring it up to the community, that should we put all of our eggs in the basket of single degree of freedom elastic system or not? Then let's talk about another big community-based project, NGOS3. It still is for coastal earthquakes. It's, as I mentioned, it is a huge database. The data is coming from Western US as well as international, Japan, Taiwan, Italy, Greece, Iran, Turkey, and New Zealand, and other locations. The project is augmented by physics-based simulations. We still need physics-based simulation with all the database increasing. Still, we would like to know what is going on in various parts in terms of source, path, basin, and other features. There are 6 modelers team involved in that one. regionalized and non-ergodic models are being developed. Both FAS, Fourier amplitude spectrum, and response spectrum models will be developed, and we are shooting to have the first major results by end of April 2025. So I cannot finish this part of the presentation without mentioning the importance of the physics-based simulations. And obviously, one key player is SCEC. Although SCEC started before the Northridge earthquake, but the progress has expanded tremendously in the last 30 years. Broadband or cyber-SCEC simulations are used not only by earth scientists, but also by engineers and ground motion modelers. They are important to understand what is going on, and interaction with physics-based simulators, especially SCEC, is growing and growing. And as you know, SCEC is now statewide. It's not Southern California Earthquake Center anymore. They are expanding to the other parts of the state. As we speak, they're trying to do simulations for the Northern California. So ground motion issues, I touched the key issues. I'd like to say a few words about fault displacement hazard. So fault displacement is a different feature than ground motion, obviously. Is very important if you have distributed facilities. For example, natural gas transmission pipelines or water distribution networks. That there are lots of cases, for example, in Southern California, that both water transmission pipelines or gas transmission pipelines, and even in Northern California, they cross faults, as well as high-speed rail. So any time that we have extended distributed facility, the issue of fault crossing becoming important. This is one example, Ridgecrest, magnitude 7.1. Yeah, the amount of the displacement, I rotated intentionally to be consistent with this figure. So you see the magnitude 7.1 rupture. The displacement goes up and down, obviously, throughout the length of the fault, and the displacement or measured displacement went up to 2-3 meters. And imagine if you have the extended facility like pipelines, obviously they will be affected. So fault displacement hazard initiative, it was another community-based large research projects. Again, 20-30 people have been involved. The goals were to develop a comprehensive and QA database of the measured fault displacement, as well as to develop new fault displacement models to be used for probabilistic fault displacement hazard analysis. The database has now 75 earthquakes, magnitude 4.9 to 8, 40,000 measured displacements. This is the slide that I got it from Alex, our key colleague and driver of the FDHI. The vertical axis shows magnitude. The horizontal axis is the 75 earthquakes that we have. The largest magnitude that we have in our database, magnitude 8 during 1911 earthquake, and magnitude 7.9 in Denali and Wenchuan. The majority of the data in our database, almost half of the data, is coming from the strike-slip fault, 35 out of 75. And then next to that is reverse, and then obviously with much smaller percentage normal faulting. The data is coming from all over the world, obviously, Western North America, as well as you go all the way to Australia and Japan and other places. There are 5 modelers that they basically finished their modeling, and they use mainly empirical data for their modeling. Also, there was a team from SCEC that they did heavy-duty physics-based simulations. It was illuminating to show some features that obviously we didn't have it in empirical data. The models are final. Multiple reports have been published, and the journal papers are being submitted. The models also have been coded in Excel and Python, and the codes are being QA'd, and hopefully we are going to release the codes by fall 2024. The cut and paste of the right-hand side that you see that I got it from Alex is an Excel file, similar to the traditional Excel files that we had for ground motion models. Now is for fault displacement. You enter the magnitude and a bunch of other the input data, as well as you choose which model you want. And if you want multiple models, weighted average, you put weight, and it gives you the fault displacement. Then another large initiative which Steve Thompson at LCI and his colleague, as well as Alex, are working on that, is to develop a statewide fault displacement hazard, probabilistic fault displacement hazard map. So similar to the ground shaking map that we have, that you enter the location, it gives you probabilistic seismic hazard analysis results. Is the same concept, but it gives you probabilistic fault displacement results close to your fault. It's an important tool for preliminary assessment of your displacement at your site. It is not going to replace site-specific investigation. It is really good for the first screening process. The simple version of the map, we are hoping to release it in fall 2024, and the more advanced GIS interactive map, hopefully we are going to have it in 2025. So this is my one before my last slide. It's just summary. So we have had major progress in quantification of seismic hazard in 30 years. Top of the line, in my view, is that initiation of multiple community-based research projects. Still, the modelers, they compete with each other. They want to do better job, which is perfect, but they communicate and they talk to each other. They learn from each other. Therefore, the entire quality of the database and models go up. We have much more comprehensive databases, fault displacement, as well as ground shaking, and so on. Models are much more robust. The physics-based simulations have greatly advanced in the last 30 years, and now getting more and more to the engineering community also. And we have had, obviously, serious progress in quantification of fault displacement hazard. So what is next? The science will continue its progress. It's really out of our control. The more earthquakes will happen, more data will become available, more models will be developed, more regionalized models will be developed, more microzonation. That is the way I rephrase non-ergodic ground motion. Is going to be more microzonation or areas in terms of ground motion hazard, because we are going to have more data, we are going to have more simulation. We can really fine-tune models at micro level, not really micro, but at a small localized level. So this is my last slide. We have a few minutes for the question and answers that obviously we are going to try to answer as much as possible. After the seminar, if you really like to communicate, you want to have some comments, you have some questions, please contact us. We love to hear from the community. It's really essential. All we do is really with the passion that everyone, it's not me only, that with the passion that we do something impactful. And with that, I thank you so much for your attention.
Thank you, Yusuf. That was a very informative talk and really illuminated how things have developed since 1994. Thank you. I don't see any questions in the Q&A just yet. I do have a few for you, if you don't mind. I wanted to ask who and for what type of applications are the models who's using these models really, and what do they use them for?
That's a good question, Sam. Let's talk about ground motion models, for example. Ground motion models are used almost for everything that is attached to the ground, for different through different routes. USGS is generally accepting these ground motion models. Therefore, the national maps are generated by USGS, and national maps are really the foundation and the backbone data for any seismic design code in the US. So if you have a single family home or 10-story building or anything else that is attached to the ground will be affected by that process. If you have site-specific case, for example, a nuclear power plant, 50-story building, and so on, you put it a little bit under microscope, but you use the same ground motion models. The impact of these models are enormous. That's why we need the community behind this. That's why each project has 30, 40, 50 people involved. For the fault displacement, generally, utilities are very concerned because of the extended facilities that they have, natural gas pipelines, water transmission pipelines, high-speed rail, and so on.
Great, thank you. You talked about sort of the advancements that are being made. You talked about directivity, ductility, and physics-based simulations. Do you see other areas where the models may get more complex, where technology might take us, including artificial intelligence, things like that, as far as modeling goes?
Machine learning and AI are coming to the ground motion modeling. Still, different groups are trying it for different applications of the developing maybe a part of a model that is coming and can be helpful. Then the other major advancement in the ground motion modeling is really so-called non-ergodic ground motion, which I called it microzonation. It used to, if you remember, you have been around 30, 40 years, you remember microzonation was a buzzword, but it didn't go much further because of various reasons. Now we have enough data to go to microzonation or non-ergodic ground motion. That is really big deal in the next N years. It's already there, but it's going to be expanded. Then within each of these things, lots of things going on in terms of how we are going to learn from the, for example, physics-based simulations in terms of for example, SCEC has been very active in Southern California. Now we are hoping they shed light in characteristics of motion in Northern California or other places. So the science will continue.
Yeah. Do they, or does anyone at some point back check these models, and how, with actual ground motion records, and much more accurate has it become since 1994 in general, do you think?
So obviously the nature is talking to us through observation. So, and obviously every earthquake, there is a surprise that the nature is revealing itself to us. So there is no way that we can abandon observation. So with all the, for example, simulations that the ground motion modelers, they did it in Central Eastern North America based on simulations, at any point they check against any even limited empirical data. They just wanted to make sure they don't violate empirical data. Empirical data is the nature, and we cannot obviously violate. So with all advances that in simulation, machine learning, artificial intelligence, everything that we do, at the end of the day, we have to make sure that we are not violating observation. We have to check it against the real data to make sure that we are consistent.
I see. A couple questions have come in on the Q&A. This one is from Santiago Caballero. I haven't checked the NGA3, so pardon me if I can't find the answer on that, but I would like to know which models will be there in the NGA3. Are we expecting the same as it was in 2014 or any other models considered?
So that's a good question. The 5 modeler teams that we had in NGA 1 and NGA 2, they continue working in NGA 3. A large new group has been added that consists of Adrian Rodriguez in Virginia Tech, Peter Stafford and Imperial College, and a couple of others, Mahdi Bahrampuri, as well as others. Is a big team that already started. So overall, we are going to have 6 teams. How many of these teams can finish the end line? We will know in the next few months. But I really see end of the tunnel. At least out of the 6, at least 3 models will be final. I'm crossing my finger to have more models. The schedule is very tight. The data is huge. And by the way, as I mentioned, we are interacting seriously with SCEC. They do lots of physics-based simulations also for us.
Great, thank you. The next question comes from our good friend Ken Hudnut. Could you please address status and plans for near-fault ground motions, in particular NGA W3 for strike, slip, and reverse faulting?
So near fault issues are obviously important for engineering applications as well as for the ground motion modelers. So various features are the data are being observed under the microscope. What can we extract? For example, in terms of directivity, which I mentioned to you, it is a still open question. We are not having a major task on the directivity. It's too much to take care of everything. But we are hoping to continue working on that one. Any feature in terms of, for example, directionality, there is one team that they are directionality of ground motion, horizontal ground motion. There is one team that they are going to examine that issue. And like anything else that we have been doing, not 6 teams, they check everything in parallel, not like that. One team is doing something about, for example, directionality. The others learn from that team. It's perfectly fine. They copy that feature, however, give a serious reference about who did it, because intellectual property. So we learn from each other. Near fault issues are top of the line for, obviously, for all of us. We don't have, we love to have more data, and lots of issues really we want to address. We will do our best how much we can do by April 2025. I'm pretty sure there will be some open questions that we won't be able to finish it, but we will continue.
Thank you. Don't see any more questions in the Q&A right now. You can also ask questions by raising your hand if you do want to do that, anyone in the audience. Any questions
Sam,
from
I have a
other, yeah, I was going to ask if Craig had any questions.
I do. I have one from Joseph that kind of comes from personal experience, having been shaken out of bed by these ground motions in 1994 and studying them after the earthquake as I worked on my PhD. There was some, at least initially, speculation that higher level intensity as a result of this fault rupture being a blind thrust fault, meaning that the rupture did not reach the ground surface. I think it stopped somewhere around 5 or 7 kilometers depth. And the confinement resulted in some experts speculating that that results in some higher level intensity shaking in the near source area. There's very limited blind thrust faulting recordings, this being one maybe the largest set. I don't know. You would know better. But I'm just curious on your thoughts about that. And does that really pan out, or do we not know enough information, or what would you say about that?
So most of ground motion modelers, they observe this. Again, the process is that you're in the middle of ocean and you're trying to really grab the trends, really ocean of data. So most of modelers, they see that up to a limit, if the ground rupture, the fault rupture doesn't reach the surface, at some frequency range, the ground motion can be a little more than counterpart with the same magnitude if it reaches the surface. Obviously, most of large magnitude earthquakes, the rupture reaches the surface because the energy is so much. But we see that the modelers, they see it generally that if the rupture doesn't reach the surface, at some frequency range is a little bit more higher than the analog version of that. But there is a limit. It's not like that you have 5 kilometers, you go 10 kilometers, you go 20 kilometers, ground motion becomes continuously larger and larger. There is a limit, at least the way that they see it in the data.
Thank you. We're approaching the end, but I do want to grab one more question. This comes from Helen Crowley. When we sample ground motion residuals for scenario risk modeling, we can sometimes get extremely high ground motions. What are your thoughts on the physical limits of ground motions, and has there been enough research on the topic, or is there more that can be done?
So, Helen, thank you very much, and we'll see you in a few weeks in the World Conference. So always, as you know well, we make a model, and either simple model or very complicated model, and we dig into the residuals, and we extract as much as possible, as much humanly possible. But obviously, there's a limit. There is a limit of the data. There is a limit of model capacity. And one feature that we are hoping that we can do a little bit better job in the next N years is that what about we use machine learning, artificial intelligence to put the millions of the residual points under microscope? Do we see something else? But that is the way it is, and we are hoping if we are at the edge of our knowledge in terms of empirical data, we are hoping the simulations to shed a light. That's why interaction more and more with the physics-based simulation is growing in the last literally 10, 20 years.
Great, thank you so much, Yusuf. This has been really interesting. I think I'm going to turn it over to Craig now. He's going to briefly talk about episode 4, and then we'll wrap it up.
Okay. Thank you, Yusuf. That was an excellent presentation and tremendous ability for questions and answers. Before we close, I want to identify to you our episode 4. This was episode 3 from Yusuf. Episode 4 will be describing the Northridge earthquake, an unexpected milestone in real-time loss estimation. It will be on July 24th. It will be given by co-presenters Ron Iguchi from ImageCat and David Wall from the USGS. And we look forward to you registering for that. You should be seeing the announcements already. When you registered for this event, you can register for the episode 4 event. And we'll be sending out more information and announcements on that in the near future, as well as our goal is to try to have one webinar per month through the end of the year, and maybe even into January, which would be the 12-month time frame since it was January 1994. So please look forward to all of those, and we appreciate your time. And we want to recognize one last time all of the co-organizing organizations that are listed at the bottom of the screen.